Good morning and happy week 2 of distance learning. We are going to finish up part 6, which is really the last thing you have to learn that's new for the AP test this year, since they cut off that last part of the course. So what we're going to do is we are going to start with a warm-up here. So I'm going to put it up and I'm going to have you pause the video, and really all you're doing here is you are looking at, it says one indicator of physical fitness is resting pulse rate. 10 men volunteered to test an exercise device advertised on TV by using it 3 times per week for 20 minutes. Their resting pulse rates were measured before the test began and then again after 6 weeks. Results are shown in the table. Is there evidence that this kind of exercise can reduce resting pulse rate? So I've got sort of 2 samples here. I've got the before sample and the after sample for these 10 men. And all I'm going to have you do is check the conditions and assumptions for doing a 2-sample t-test with these results. So pause video, do that, and then if you turn it back on in a couple minutes, it will tell you about what you should have seen. All right, so condition number 1 that we check for our 2-sample T is we are looking to see that we have a random sample or random 2 samples, essentially, of men. Now, it doesn't say that. It says that there's 10 volunteers, and so instead of it being random, I need to make the assumption that those 10 volunteers are representative of all men. Okay? Second thing, though, that becomes a problem is that for a 2-sample T inference, my 2 samples have to be independent of each other. But if you look at the 2 samples, I have a before and after resting pulse rate for like 10 men. And so if I know something about their before pulse rate, that probably is going to tell me something about their after pulse rate. Like, you're probably not going to start with a before rate of 91 and end with an after rate of 73. That's a huge drop. And so we're missing that independence piece. And so a lot of times when you have sort of a before and after is really, really common. You'll often see like twin studies are 2 samples, but they're paired data, looking for 2 things that are related in some way. Husband and wife, siblings. Whenever you have 2 samples that are sort of paired intentionally at the same sample size, paired to have equal things paired together, or one person before and after paired together, that's what we call not a 2-sample t-test, but a matched pairs t-test. You essentially have pairs of data that match together in some sort of way. In this case, it's before and after. So what I'm going to have you do is pull out that note packet. You're looking at chapter 24, which is likely our last chapter that we do direct instruction for until after the AP test. We'll see how things shake out here. But here we go. Grab your note packet, pause if you need to. I'm going to get started. So up at the top, your essential question is, how does the paired t-test change with matched pairs sampling? And so what the difference is here is we're not using 2-sample t-tests for paired data because the paired data come from samples that are not independently chosen. They're purposely dependently chosen, in fact. If we know that the data are paired, we can examine that paired difference with each pair, the difference between them. Because it's that difference that we care about, we treat them as if they were the data. The difference is the data, and ignore the original 2 sets that we have. So basically, you're going to take your 2 sets of data, subtract them, end up with just 1 set of data that is the difference between the first and the second, and then you're going to do inference on that 1 set of data of the differences. So, again, now we only have 1 set of data to consider. We can return to that simple 1-sample t-test. So we're going to go back to what we did when we were all together in school, that 1-sample t that we reviewed last Monday. And mechanically, a paired t-test is just a 1-sample t-test for the mean of the pairwise differences. And you'll see kind of what that looks like when we come back to that resting pulse rate example. And the sample size here, n, isn't the number of data in the original 2 sets, it's the number of pairs that you have together. Okay? So, the inference here isn't going to feel much different, except that we are talking about 1 sample of difference data instead of multiple samples or 1 sample of data that isn't difference data. And so our parameter is going to be mu, and I usually put a subscript d with it to be the mean difference between whatever my two variables are. And then you're going to have some hypotheses. Your null hypothesis is that the mean difference equals something. Now, typically what would be boring is, if you think back to that pulse rate example, what would be boring is if the exercise program isn't working and the before and after are the same. Or if I was doing a twin study, like, what would be boring is if there's no difference in, like, how a treatment works on twin A versus twin B. And so typically that difference is 0. That would be the boring situation, is if the two paired populations are the same, and which would lead to a difference of 0 when you subtract them. Again, your alternative hypothesis can go one of 3 ways. It can either be a not equal to, a less than, or a greater than. And you're going to check assumptions that kind of match what you already did back in chapter 22 for the one sample t. Assumption and condition number 1 is you want a random assignment of treatments, or you want your data to be representative of the population you're trying to say something about. Number 2, you want your paired data to be a large enough sample. Actually, that's the third one. Number 2 is that you want your pairs to be independent of each other. So each set of 2 things should be independent from one to the next. So again, we'll talk about that more with your resting pulse rate data in a minute. Number 3 is the one I almost got to ahead of myself, where you want your sample to be large enough. And so your data distribution of the differences should be roughly normally distributed. And again, the more pairs you have, the less normal it has to be. The smaller your set is, the more symmetric and unimodal you want to check for. If all of those necessary assumptions and conditions are met, we may proceed with the matched pairs t-test. Your degrees of freedom is n-1, but again, n here isn't the number of total data points that you start with, it's the number of pairs minus 1. All right, your test statistic is going to look like the one sample t-test statistic again. You start with your mean difference from your actual sample, subtract the difference from the null hypothesis, that's the one that's usually 0, and then all divided by that standard error, which is s over the square root of n, or the standard deviation from your sample of differences, divided by the square root of n, which is number of pairs. And so that formula is, again, we're starting with our sample minus the hypothesis over that standard error, and those test statistics are always found in that same sort of manner. Okay, and then you're going to obtain your p-value. There's 3 ways you can do this. Again, we've been talking through these before. You can do a TCDF in your calculator, lower bound, upper bound, and then degrees of freedom. You can use the table in your green packet or your textbook, or you can do it in your calculator by pressing stat and then going over to test and just doing a t-test. Okay, so all 3 of those ways you can find a p-value. And then last but not least, you're going to make your decision and state a conclusion in context just like you're always used to. So these are all these possibilities are in the spot that would correspond to the same spot. Here's what I mean by that. I wrote, since our p-value is low or high, so the first one coming up and all the next sets of blanks goes with low. If it's low, you reject the null, and that means there is evidence of that alternative hypothesis being true instead of your null. Or if the p-value is high, you fail to reject the null, which means there's not sufficient evidence of your alternative hypothesis being the case over the null. Last thing we need to talk about is how this process differs if you're making an interval, and so you just need that interval formula. Again, you start from your sample statistic is always going to be the center of your interval, adding and subtracting that critical value, and remember you can get that t-critical either by doing inverse t on your calculator or your new calculator simulator, or in your table in your packet. Remember where we have those confidence percentages down at the bottom, and then you go up to your degrees of freedom using that t-table. And then you've got that standard error formula. One thing I just want to refresh in your mind one more time is that back half of the formula following the plus or minus is your margin of error. So anytime a question is asking about margin of error, it's using everything that comes after the plus or minus, the critical value times the standard error, and the standard error is that last piece as well. Okay? we're going to do an example. We're going to do that example in your notes together. Before we do that, though, I'm just kind of curious who's watching all these videos and listening carefully, so I'm going to offer you a little Easter egg here. If you are still listening, if you are watching this video and email me by 11:59 on Monday, I'm curious because I miss seeing you guys and talking to you on a daily basis. I have been trying to kind of spend my time doing productive things as much as possible. Don't get me wrong, I've binge watched my fair amount of TV, as you guys know I do anyway. But I'm going to give you 2 hobbies that I've kind of picked up since shelter in placing in my tiny apartment. And those 2 hobbies are, I've been trying to sort of reteach myself Spanish using the Duolingo app on my phone. And I've also been doing nightly yoga. Some of my friends have started a 30-day yoga challenge. So those are 2 of my hobbies. So if you, by 11:59 tonight, email me with a hobby that you have been spending a lot of your time doing in your downtime, I'll give you a couple bonus points in the old grade book. Since I don't really grade you guys on these video days, I just kind of want to see who's still checking in or who's just fast forwarding through my videos. So there you go. All right, let's move on and let's do this example. We've got that resting pulse rate example that we started with back in the warm-up. And so we already kind of know it's violating that principle of having independent samples of each other, so we can't do that 2-sample t-test. We've got pairs instead. And so when I'm looking at this problem, it says 1 indicator of physical fitness is resting pulse rate. I already read this problem to you, so I'm not going to do it again. I'm underlining some words that are jumping out to me as I'm reading it. Number 1 is the word volunteer. I'm going to have to address that when I talk through assumptions and conditions. I'm looking for, is there evidence that this kind of exercise is reducing resting pulse rates? That's going to give me an idea of which way my alternative hypothesis should go. And then I'm underlining, if so, how much, to remind myself that if I decide that I'm rejecting the null hypothesis, I want to also make a confidence interval to figure out by how much. And so here we go. We're going to run through the phantoms process. Before we do that, I'm going to have you grab your graphing calculator or on your Chromebook on that little TI app. Type in all of the before pulse rates into your L1 and all of the after pulse rates into your L2. So you're going to press stat, enter, and type all those numbers in. If you need to take a second to pause, go ahead and take a second to pause, and we'll still talk about that parameter step that popped up. Okay, so what we're trying to say something about is the mean difference in the resting pulse rates before and after the program. I want to know what happened. Did exercising more slow down the resting pulse rates for these 10 men? And actually, really what I'm trying to do is generalize that to all men in whatever population they're talking about. So that's your mean difference. That's your parameter that you're defining and you're trying to say something about. Before we write hypotheses, I want you to gather some data. So I'm really not looking at either of these 2 data sets individually. What I want to look at is what happened to the difference when I subtract the before minus the after. So I'm going to have you click on your calculator back into your list, so you're looking at your L1 and your L2, and then I'm going to do this with you so I make sure that I explain it well. You're going to go up, take your calculator arrows, and highlight L3. Hopefully your L3 is empty right now. Go ahead and hit enter. And you should see your cursor flashing down at the bottom of your screen now. It should say L3 equals. And you're going to subtract the before minus the after. So you're going to write L1, so second 1, minus L2, so second 2. And then hit enter. And you should see that list get populated. And you should see that it's like 0, 4, 4, 1, 4, 8, 3, etc. all the way down. It did the subtraction for you. Now you also could instead go ahead and subtract those by hand if you wanted to, and then just type this whole list into L1, this difference list. There's only 10 pairs, so it wouldn't take you very long to do it by hand either. So your other option is to literally go through and subtract 73 minus 73. Oh, that's 0. type that into L1. 83 minus 79, well, that's 4. Type that into L1 and keep making your list. But I find that when I have a bigger set of data, rather than subtracting them all individually, or if they're not easy subtraction problems like these ones are, it's sometimes faster to just type them in and then let the calculator make the list for me. So I'm going to do the rest of this assuming that you did what I just told you to type in and that your differences are in L3. It's going to change some of the ways that we type things into our calculator. But if you would rather just clear everything out, type it into L1 that you're used to, feel free to do that as well. So what we're going to do is we are going to write our hypotheses. The null hypothesis, what would be boring, is if this exercise program does nothing. And so that would mean that mean difference, if the pulse rates don't change from before to after, then when I subtract them, I'm expecting to get 0. If it's 73 and 73, I subtract those at 0. If it's 80 and 80, I subtract them and it's 0. And so that's where I get my null hypothesis from. I kind of messed up out of order here. So before we write our hypotheses, I guess, I was going to have you guys find your one variable stats on your calculator for L3 because we're going to come back and need that later. So go ahead and run your one variable stats on L3. So here's what you're going to do. You're going to press stat. You're going to go over to calculate, hit enter on one variable stats, and then before you hit enter here, we are trying to get the statistics about your differences. And so you're going to press second 3 to get L3. You should see an X bar, you should see your SX, and you should see N. And so go ahead and write those 3 things in. Hopefully you got 2.8, 2.53, and 10. Okay, now we're going to do our hypotheses. So we already talked through that null hypothesis that the mean difference would be 0. Now, I need you to think carefully about this alternative hypothesis because it's kind of tricky. If I subtract the before minus the after, the question is, do I have evidence that heart rates are being reduced? If they're being reduced, what that means is that the after is smaller, is lower than the before. And if the after is a smaller number than the before, I want you to think about, would those differences be positive or negative? And then is that greater than 0 or less than 0? And put that into that alternative hypothesis. Hopefully you got a greater than, that's what it should be, and now we're going to check our assumptions and conditions. So again, we have kind of a problem here. It's not a random sample, but we're going to assume that these 10 volunteers represent all adult men. We have to make that assumption, otherwise it's over, we can't do inference. We don't want that to be the case. I know you guys don't want to have to stop this problem right now, and so we're going to assume that that's true. Number 2, I need matched pairs, which I have, and each man's resting pulse rate should be independent of the next. Knowing one person's resting pulse rate shouldn't tell me anything about the next person's resting pulse rate. And then number 3, you're going to do a histogram of L3. I want to check to see what does the histogram of the differences look like. So you're going to, in your calculator, press second y equals to go to the stat plot. You're going to turn plot 1 on. Make sure it looks like a histogram, and then instead of your x-list being L1, your x-list is now L3. That's where your differences are. And then you're going to press zoom 9 and take a look at that histogram. Now, you're going to see something that looks like this, okay? It's relatively symmetric. 9 of the things are sitting in a block like that, and one of them is off to the side a little bit, but it's normal enough. It's relatively symmetric, pretty much unimodal. It is unimodal. And then that means that my sample of 10 is going to be large enough. With all 3 of those assumptions checked, we can do a matched pairs t-test. And my degrees of freedom is the number of pairs minus 1, which is 9 in this case. And that means we're going to calculate our test statistic. So we start with the mean from our sample, which that x bar was 2.8. minus the null hypothesis of 0, and then all over that standard deviation of 2.53 divided by the square root of 10, standard deviation 2.53, all over the square root of 10. Go ahead and type that into your calculator. And that should give you a test statistic of 3.5. And then we're going to go ahead and find that p-value. There's a couple different ways you could do this. You could, in your calculator, do a t-test of L3. It's data in L3. Or you could do TCDF from 3.5 to 1,000, because we're doing a greater than alternative hypothesis test, comma 9 degrees of freedom. Go ahead and find that p-value. Should be 0.003, and then you're gonna stop. Why don't you try to do this? I think you can do this part now that you have that p-value without me. Go ahead and make your decision and write your conclusion. So, because the p-value is low, we reject the null hypothesis. That's the decision we're making. And then we put that conclusion or that decision into context, saying we do have sufficient evidence that this exercise program that these men are doing reduces resting pulse rates in men. So this exercise program is proven to reduce resting pulse rates in men. Okay, then we go back to the question that says, if so, how much? And so we're going to make an interval, a confidence interval, with degrees of freedom 9, a match pairs t interval. Again, you start your interval with that x bar in the middle, 2.8, plus or minus. I need to find a t-score, and let's go ahead and use 95% confidence, because that's what we tend to do if we're not given a value. And so I'm looking for 95% confidence with 9 degrees of freedom, and so you can use your table to do that, or you can do inverse t. If you do inverse t, you're not typing in 0.95 as the area. Remember, it goes from 2.5% to 97.5%, and so you could use either of those as your percentage. So you would do like inverse t of 0.975, comma 9. And that, either way, the table or the calculator should give you about 2.262 as your t critical value. And then times that standard error. So the 2.53 standard deviation divided by the square root of 10. In your calculator, you can either math it out from here, it's not too bad, or you can do in your calculator a stat test t interval of L3. Either way, you should get an interval that goes from about 0.990 to 4.610. And then you're going to write a conclusion that says, I am 95% confident that the true resting pulse rates were between 0.99 and 4.61 beats per minute higher, I can't spell the word higher apparently, before the program than after. Okay. I believe that's all I've got for you. You are going to, real quick, if you didn't already read on Google Classroom, you're going to go and add match pairs to your little cheat sheet grid. And then tomorrow, you're going to do a little bit of digital practice and get some time to work on your homework packet. Okay? Don't forget what I told you in the middle of the video to do if you haven't done it yet. All right. Bye, everybody.